Okay, so any questions before we go on? Okay, so before we discuss the resonance, now in actual life, if you look at this one, we have seen that for a pendulum, the energy is always conserved. So if you just release this, start this pendulum to oscillate, it should continue until infinity. But as we see, it doesn't go until infinity. After a finite amount of time, the oscillation just dies away. So the energy somehow gets reduced. Energy is not conserved. This basically tells us that there is some dissipation in the system. And that dissipation in this case will be the drag force. So if you just take that example, or if you just imagine a spring, basically this was the equation that was governing the motion. Mass times the acceleration was equal to minus k times x. This is in the absence of dissipation. Well, in the case of the spring, this is the spring constant, this is the mass. In the case of the pendulum, this is the moment of inertia, this is the angular velocity times the weight of the object. Now this is the weight of the object, this k. But mainly the equations, the mathematical equations would be identical. Now furthermore, if we have a drag force, the drag force depends on the velocity, and the simplest description we could have minus gamma times x dot. But here x dot is dx by dt. The number of dots just denotes the time derivatives. d squared x by dt squared. It's just a different notation for the same thing. Whenever you see a dot, it corresponds to a time derivative. Or the equation will be mx double dot plus gamma x dot plus k over k x equal to 0. Well, this is no longer a harmonic function. The motion will not be harmonic. In fact, if you solve this equation, you will see that the x can be written in this form. It will still have some amplitude times e to power minus b times t. So you can just imagine that the amplitude of oscillation just dies away. With exponential, it will go to 0 times your harmonic function. Plus 5. So this will be the solution. So of course you can relate this b and omega prime to these m, gamma, and k constants, which you will do in the homework, but for the time being, for us, it will be enough to know that the solution of this equation will have this form. And then the next question is, so what does this form tell us about the motion? Now, one thing is, okay, this form is of course true if gamma is sufficiently small. Now, what does this mean? Well, this omega prime, remember, if there is no damping, this is what's called the damping. If gamma is 0, omega, we already know that it should be square root of g over L. This is what gamma would be. Now, if you have these coefficients, let me check. Okay, so this is minus gamma squared divided by 4m squared. So this is the exact frequency. Now you will derive this equation. And this is something that you should do once or twice in your lifetime. It's your first year, you will do it. So if gamma is small enough, then this under the square root you have this positive number, and that's the new angular frequency appearing over here, omega prime. Also, it's not a big surprise that the angular frequency is now smaller than before, or the period is larger than in the absence of dissipation, because what dissipation does is it will be slowing down the motion. So if the motion is slower, then it will take a longer time to cover a certain distance. So that's why we expected that the frequency of oscillation for a damped oscillator would be smaller than the frequency of an undamped oscillator. Now this is just a harmonic term that we had already studied to some extent, but then if we can somehow imagine this whole thing as our amplitude, but now the amplitude depends on time. So this is how the amplitude will change in time. And with this amplitude, my object will be just oscillating back and forth. And this is actually what we observe over here. Well, it's still oscillating, so the damping is quite small. But you see, the amplitude very slowly goes to zero. Now there are a few other cases. This is the solution if gamma is sufficiently small. Now there are cases when gamma becomes very large. Well, if gamma is very large, then the motion will be, is it here? This is the amplitude, how the amplitude changes. If gamma is small, this B is proportional to gamma. So if gamma is small, the time dependence will be small. So that's why here I draw that amplitude changes very slowly compared to the oscillation. So before the amplitude changes significantly, my system oscillates a couple of times. Now if gamma gets larger, that means the amplitude will decay much faster even before my pendulum or my oscillating system makes one full cycle. So if the amplitude just goes to zero before my system oscillates, so this will be what I will observe. Sorry. So this is what we call overdamped. So it's too much damped. This is what we call underdamped. Plus there's the critical limit between these two. Well, it almost makes an oscillation but fails to complete one oscillation. So it will make one oscillation but almost fail. So this is what we call the critical damped. Okay, the next time you go to your car, if you have one or one of your relatives or parents' car, try one thing. Go and sit on the front of the car, jump back, jump down, and see how the car oscillates. Or you can just push the front of the car down a bit, just release it and see whether it oscillates or not. If it's oscillating, you see, you went to the car, you pushed it down, you released it. If you push it down, when you release it, it will go up. If it keeps oscillating, then tell the owner of the car that they should change their suspension. Because that's the suspension system in the car that is mainly uses what we call these critical damped oscillators. The basic idea of that suspension. So have you ever ridden a car that doesn't have a good suspension? Well, most of the buses we have, they don't have a good suspension. So if you go with a car that doesn't have a suspension, you will feel every jump on the road. So even if the car goes over a very small rock, you will feel it, because it will be just like a rigid body. And if you are on a rigid body, when the rigid body moves up, you will also move up with the rigid body. Now what the suspension does is it's just like a spring between you and the rigid body. So if the rigid body moves up, the spring will not push you up immediately. So it will just push, it will take some time. And during this time, the spring just goes back. The rigid body goes back to the initial configuration. So if this time of going up and down of the rigid body is very short, then you practically will not feel anything. But if you do this with an actual spring, the wheels go up and down, and after that the spring just oscillates. So you will start oscillating. And that's also not something that you want. So one is the under-damped case, the other one is the over-damped case. What you would like to feel is when the wheels go up, you might go up a bit, just a very slight amount. When the wheel goes down, you should go down and stay there. That's what you would like to have. Of course, you would like to extend this period of time so that you will not feel a significant force. Remember, the force is the spring shouldn't be able to push you too far. So that's what we call the critically damped case. It doesn't stop right away. It doesn't keep on oscillating. So it is the longest possible time that you can stay without actually oscillating. Now let's see a video of this damped thing, of this damped oscillator. Okay, here is the oscillator we have. Now to create this damping effect, So here you have a cup filled with oil. Then you have this spring, there is a mass attached here in the oil. Well, the oil is used so that it creates a large enough damping so you will be able to see the effect in a short amount of time. Now let us follow the motion. Okay, we can follow this red dot, the black dot. Okay, this is the black dot that we will be following. Okay, so Murphy is back in business. Okay, so let's just watch the video. So just follow this stuff. So this was the initial amplitude, somewhere over here. It is getting smaller and smaller with time. So this is what we call the underdamped, because the oscillator makes a lot of oscillations before it almost completely stops. Now it practically stopped. So this is an experiment you can also do at home. Now this will be the more realistic oscillating system, because the damping will be always there. Now, any questions on this one? Now there's one more oscillating system that I would like to discuss, which will be what's called the driven oscillator. Now in these examples, what we had considered was there is a gravity in the pendulum case which creates this restoring force, but once we release the object, we are not exerting any force on the object. But in the case of the swing, for example, we are also exerting a time-dependent torque on the system. So that's what we call a driven oscillator. Now, before we go to the driven oscillator, any questions on these ones?
Exactly beside that, harmonic motion is over.
It will never be over. It will become very close to zero. It won't be unobservable. Ideally, of course, it will never be over.
It's unobservable.
If you look at this plot, the amplitude becomes very small, but it never becomes exactly equal to zero. In your calculus course, you don't see complex variables, right? So are you familiar with this thing? You are familiar with this? How many of you are familiar? How many of you are not familiar with this equation? Okay, so one derivation plus, then I can use it in the homework. Okay, so let's look at driven oscillators. First, let's ignore the dissipation. Let's assume that there is no driving force. This is the equation if you don't exert an external force. Now let's just imagine we are exerting some external force on the system. It might even be time dependent. Or mx double dot plus k times x is equal to f external times t. Now just to make things a bit simpler, I will assume that this external force is also harmonic with frequency omega. This omega is just an arbitrary number. I will call omega 0 squared to be k over m. So this is the equation satisfied by my oscillator. There is an external force acting on it. Well, you can say that this is the equation for the pendulum. I is the moment of inertia, x is the angle, and this is the external torque that you are creating. And we had just said that the torque that you create has a frequency that is equal to the frequency of the pendulum itself. But in this case, this frequency can be arbitrary. And we will see that if this frequency is equal to the frequency of the pendulum, in that case we see that buildup of the amplitude. Now again we have this differential equation. I will not go into how to solve this differential equation. You will study them in more detail next year. But I will just write down the solution. So x of t is equal to a cosine omega 0 t plus phi. This is as if this driving force is absent, plus f0 over k minus m omega squared cosine omega t. Or we can also write this as x of t is equal to a cosine omega 0 t plus phi plus f0 over m 1 over omega 0 squared minus omega squared cosine omega t. Well, this is not that interesting. I mean, this a and phi you have to determine by the initial conditions. What is the initial displacement? What is the initial velocity? But once you are given the initial displacement and initial velocity, then you know what A and phi is, but this is the term that's more interesting for us. You see, the amplitude of this, here we have basically two different harmonic oscillations. There is one harmonic oscillation over here, another one over here. With this, the frequency of this additional term is equal to the frequency of the external force. The amplitude is important. You see that if omega and omega 0, remember omega is the frequency of the force that, or the external force or the external torque that you're applying, and omega 0 is the so-called the natural frequency of your oscillator. If they match, if omega and omega 0, they become equal, you see that here we have, this term becomes infinite. Of course, this solution is not valid if omega is equal to omega 0. Now, this is the solution if omega is not equal to omega 0. You can still find the solution when omega is equal to omega 0. And when omega is equal to omega 0, the solution is similar, but we have this term. Now this is the solution when omega is equal to omega 0. And you see that, okay, this is our harmonic oscillation. So our system will still oscillate back and forth. But what's happening over here is we have this amplitude of the oscillation which is increasing linearly with time. So this is in fact why in the swing, when you go back and forth with the same frequency as the swing itself, your amplitude grows in time. It will increase. So even if you start with a very small oscillation, the amplitude will get larger. So why does it get larger? Okay, so this is all the mathematics about why it gets larger, and you will know how it gets larger with time, but why does it get larger? If the frequencies match. Okay, so you see, we have all these, we have studied all these dynamics, mechanics, we know what the force is. So let us just follow step by step what's happening in my oscillation. So let's just say that initially, just for simplicity, my object is over here. It is oscillating between these two limits. My object is moving in this direction. Let's say that the force is also in the same direction. So is the force doing positive work or negative work? It's doing positive work. And as long as the velocity and the force, they are in the same direction, they will be doing positive work. And when it reaches over here, it stops. So the force, and then it will move backward. But if the frequencies match, the force also changes its direction. So if the frequencies are matching, at a given point, the work will be either always positive or either always negative. In all this, in every case, the total energy of the system will change linearly with time. So because you will be always doing positive work. Of course, if you have a constant force, like we had also studied the example of a gravity acting on a spring, if you remember that one. On Tuesday, we studied this example of this one. Gravity is always pointing downward. So as the object is moving down, the gravity is doing positive work. As the object is going up, the gravity is doing negative work. So during the cycle, the gravity doesn't do anything. But if as the object is going down, the external force is also going down, and when the object is moving up, the external force is also pushing it up. The external force will always do positive work, And since it's always doing positive work, it will increase the energy of the system all the time. So that is why if the frequencies match, in that case the energy of the system will increase. Now if they don't match, what will happen is in one cycle, when the mass comes to this turning point, the force, after this turning point, the force will be doing positive work. In the next cycle, it will be doing negative work. In the next cycle, it might be positive or negative. So the work done by this external force will be both positive and negative. So that's, in that case, the amplitude will not increase, but it will be just oscillating up and down. It will be changing. And in the long run, it won't be doing, the average energy of the system will not really change. Questions? Okay, now let's come to we have the driving force plus the damping plus gamma x dot plus kx, this is F0 cosine omega t. And again, the solution of this system will be, there will be one part which will be independent of F0. But you see, if you wait long enough, this part will just go to zero. It will not influence the general motion of my oscillation. The important part will be the next one. Okay, I don't remember the expression for this delta, but this delta can also be written in terms of this one. Now here, this term, if you wait for a long time, whatever the initial conditions are, this will be irrelevant, because they will go to zero with time. But this term will not go to zero even if there is damping, because although there is damping which tries to take away energy, there is also this external force which will be giving in energy to my system. So the energy of my system will never go to zero. Now, one interesting thing will be, how does this function look? Let's just call that function I omega. I omega. Here I have an omega squared. I omega will be F0 over square root of m squared omega squared minus omega 0 squared plus gamma squared omega squared. So you see, we have this denominator over here. Now the denominator becomes, well, you see, this term is positive, this term is always positive. Now this everything is also squared. I have the sum of two positive terms, and the minimum value of this number, denominator, will be when omega is equal to omega 0. This term will be 0. It will be close to that one, not exactly at that point due to this term, but it will be very close to omega is equal to omega 0. And when omega is, for example, very large, in fact, this term will not be there. It will just go to 0. So this I omega basically have such a shape as a function of time, no, not time, as a function of omega. But for very large values of omega, it goes to 0. There is a value close to omega 0 where it becomes very large and then dies away. So this is where we call the resonance. Now, compared to the previous case, when there is no damping, in this case, eventually the amplitude goes to infinity, it diverges. It goes up to infinity. But in physics, nothing can be infinite. So what is missing over here is the friction force or the drag force. Because if the amplitude goes to infinity, that means the velocity is going to infinity. So you just get the drag force is proportional to the velocity. But if the speed is infinite, you just cannot ignore the drag force. It has to be there. And when you add the drag force, there is no infinity left. Everything will remain finite, but of course the amplitude can become very large. Now, if the frequency is very large, you basically don't feel it. It has practically no impact. Well, this is in fact one of the reasons, for example, the lights over here in this classroom, they are blinking like 50 times a second. But that blinking effect is so fast, the frequency is so fast, that it doesn't really create any visible effect in our eyes. So we cannot notice it. Of course, unless the lights are bad, and you do have these fluorescent lamps whose flickering you can actually see, they become disturbing. But for a fluorescent lamp that's working properly, you will not see it, you will not feel it. Or when you measure the electricity, next term you will be doing experiments with electricity. The measuring devices, the electricity that we are using, they are oscillating so fast, the measuring devices we have, they will not feel it. They will not feel the oscillation, they will just tell you an average value. Or if you compare it with this one, they will not see this very fast oscillating piece, they will see some average value. Now, any questions on these oscillations? Of course, once we have the time dependence of the oscillator, we can calculate the time dependence of the kinetic energy, of the potential energy, etc. Any other questions? No questions? About anything else? There's too much time for a quiz. This is the question. So you have a spring whose length can change, and then you have a mass attached to it. Now, since it's a spring, its length will change depending on the necessary tension force or the central force that is necessary to keep the object in circle. Well, it won't be a circle, it won't even be a circle, it will have such a shape, an egg shape. So this will be basically the shape of the motion. Because there is also gravity, and the object is moving down from this point down to here, its speed is increasing. So at this point, at an arbitrary point over here, you can imagine that it is making a circular motion around a circle of radius, let's say large r. So as speed is increasing, so the necessary central force will be larger, the speed is larger. So the spring should get longer, because the force that the spring exerts is proportional to the change in its length. So if you want a larger force, you should extend it longer. Now the motion will get complicated. And I cannot say that whether what will be its shape, etc. But the basic thing that you have to do is just at some point over here, what will be its speed, and if its speed is a given number, then what should be the length of the spring? That you should study. So you can actually find the length of the spring as a function of the angle it makes. Because if you know this angle, let's say if you know this angle and the initial speed, let's say at the top it has a speed v0. At this angle you can determine what the speed will be, and if you know what the speed will be, you can determine what should be this length. So at a given theta, you know what the length is, and from that information you can obtain the shape of the circle. Okay. The trajectory.
Can we calculate the motion of next to pendulum?
Well, let's say that is one of my favorite questions in the graduate qualification exams. So the question is basically this one. You have one mass, you have another mass, right? You can. That's all I will say about that. I will not try to solve it.
Was it similar to spring mass attached to a spring and mass? Again.
This one. You might have the walls, you might not have the walls, but it will be similar. More or less the same thing. But I will not go into that. No, you will study them in your third year. This is also another problem that you will study in your third year. Other questions? Not necessarily with the about the oscillations. You don't want to listen. Tension? No, pressure. But we didn't study the pressure. Pressure is just like the tension in a string, but for the gases. It doesn't have its own direction. But you see, if you have a string that has a tension, the tension is just a number. But if you want to calculate the force, let's say, you have this object over here, you attach it by a string that has, this is the tension. The force that this exerts on this mass will be tangent to the string, and its magnitude will be equal to the tension of the string. And if you have another object over here, the force that this feels will be also parallel to the string, and its magnitude will be equal to the tension. So the tension kind of tells you the magnitude of the force. Just like pressure. Pressure gives you the magnitude of the force acting on a surface. The direction, if you have this object, this volume filled with a gas at a given pressure, there will be some force acting over there. This is the direction of that force. There will be a force acting at this point due to the pressure. This will be the direction of the force. But this direction is not the direction of the pressure. Pressure doesn't have a direction. Okay, let's do an example about collisions. Suppose you have an object of mass m. You put it in a cube. This has the length L. So what is the time between two, and it is moving with a velocity v, with a speed v in this direction. Now what is the time between two collisions? with this wall. So it hits this wall once, bounces back elastically, then it goes to the other wall, hits it again, comes back, and the time between these two collisions. Well, it covers a total distance L, 2L, L on one side, L on the other side. Since the collision is elastic, the speed has to be conserved, the same before and after the collision. So the delta T will be just 2L over the speed, v. So how much momentum is transferred to the wall? Well, before the collision, the momentum of this mass is mv. After the collision, it is mv in this direction. Now the change in the momentum of my mass is 2mv in that direction. So the change in the momentum of the wall should be 2mv in the other direction. But the magnitude, in any case, will be 2mv. So what about the average force? Remember, the average force is delta P over delta T, which is 2mv divided by 2L over V mv squared over L. Let's say of one of these point masses. Now let's assume that we have n of them. Well, if we have n of them, each one will exert this force on the average. The total force will be, of n of them, will be n mv squared over L. Well, your friend was asking about the pressure. Now, pressure is defined as the force over the area. Now we are imagining we have this cube. So this will be n times mv squared over L times A. Well, L times A is just the volume. So we have pressure of this, let's say, gas. What we are imagining is we have n point-like objects moving with velocities with a given speed v. So they will exert the force on the wall, the pressure exerted on the wall times the volume of the object as a whole is equal to n times m, let's say Vx squared. Why Vx? Because we are assuming that it's moving in the x direction. So already we show that PV over n will be equal to mvx squared. Well, of course, this is the average value. And this will depend only on temperature. We will assume that this is constant. So what's the name of this law? I always forget. I don't know. You should already remember this from your chemistry course. So PV over N is constant. In fact, that constant you define as some other constant times the temperature. This is the definition of the temperature. This constant over here, you define as some constant. This is also some other number. times the temperature. And this is not a derivation, this is the definition of the temperature. So you start with just basic knowledge of general physics, you can derive almost the ideal gas law.
When we are calculating the average force, we divided delta P over delta T.
Yes?
In that I think that delta P is happening in a collision time, but delta T is not the collision time.
Well, you see, the actual force of one particle as a function of time, as your friend points out, it's just colliding at a very short amount of time. So this will be the force as a function of time. But I can still represent this by some kind of an average force. The average force is this one. This is just the average. Now just imagine it like the speed or the velocity. We had defined the instantaneous velocity, we had defined the average velocity. Now the instantaneous velocity can have a huge magnitude depending on your motion. But nevertheless, average velocity could have a very small magnitude. I mean, you might start here, run very fast to the back of the class, run to this side, to the other side, and come back over exactly at the same point. Instantaneously, you might have a huge speeds, but your average velocity will be very small. Now, of course, here your friend still has one point. This is something we measure. We don't measure this one. So because we don't have just a single molecule, what we actually have, if we had enough sensitivity in our equipments, we would have measured, okay, one collision, the other one, the other one, other one, other one, etc. So they will be oscillating very fast. So what your equipment will measure will be this one. You will not be able to measure these peaks. Nevertheless, this force is almost constant. The one you will measure will be constant. And when you think of the total momentum transferred to your ball, it should be the same. I mean, this will be either you sum all these peaks or you sum the averages corresponding to all these peaks. You will get the same number. Now, this relation will still be valid to a very high precision. Although you are right, the actual force for a single molecule will have this shape. But the average for us will be good enough if we are summing all of them. Okay, see you next Tuesday.